All right, so just so that we're all on the same page, I skipped 2 slides here. I skipped the practice problem 11.10 slides just because, again, this module is getting really long and I don't want to just continue to bog you down with more videos. If anybody wants to see me solve that one, feel free to let me know and I'll make a separate video on it in the future. But for now, I'm just going to move on to maximum average power transfer. I'm going to cover this pretty quickly. So for DC, maximum average power transfer, I didn't talk about this in 220. But for DC circuits, if I have some kind of a circuit here, most of the time, my voltage source or whatever I'm using to supply power to my circuit is going to have some source resistance. We can call that RS, okay? And so what I really have is not an ideal voltage source, but I have a voltage source with some series resistance, parasitic, that's connected in series with the voltage source. And what that means is that if I think I'm supplying 5 volts to my circuit and I have a small series resistor here, note that the voltage here will not necessarily be 5 volts. As soon as this starts pulling current, I'll have a little bit of a voltage drop across RS. And so what I'll really get here is 5 volts minus I times RS. So if RS is really large, my series resistance is really large, then I will lose a significant chunk of my voltage. But if my RS is really small, then I won't lose any, right? Because if RS goes to 0, then this term goes to 0 and I have 5 volts that I'm supplying, okay? So that's important to note. And so a lot of these maximum average power transfer questions are going to ask what is the maximum, what value for load resistor can I connect to my circuit to maximize the average power that's transferred? In DC, it's very straightforward. It's just the value of RL that is equal to the value of RS. It's quite interesting that might be the case. You might think that larger values of RL would maybe result in less current, and so we would have the maximum average power transferred, or smaller values of RL would result in more current, so that would give us more maximum average power transfer. It turns out that if RS and RL are equal to each other, so power max is in the case where RL is equal to RS, okay? So if my source resistance, and so you'll see this all throughout circuits, you'll see sources like your function generator in the lab that will have a 50 ohm source impedance. And if I want to deliver the maximum average power to my load, I need my load to match that, which I basically am saying that I need my load to be 50 ohms as well. And that it doesn't result in the maximum voltage here. Note that it's not the maximum voltage by any means. It's the maximum power that is delivered from the source to the load, okay? So that's the key there, is that it's not, because obviously the larger that we made this value, right, the less current would flow, and so we would get a very, very, very small voltage drop across that resistor. The smaller that we made that value, we would get a very large voltage drop across that resistor, or vice versa. I said that backwards. If we made this value really, really, really large, we would get a huge voltage across it, close to 5 volts. If we made it really, really, really small, we'd basically have 0 volts across it, and all the voltage would be dropped across the source resistance. So it's not about the voltage, it's about the power. And so note that the maximum power is transferred when the load resistance and the source resistance are equal. Okay, so that's the important piece for DC. For AC, it's very similar, but we have to take into account impedances now, which are, changing with frequency. So we've got some kind of a source, some kind of a source impedance, similarly to our source resistance that I drew. So this will be Z source. Might not necessarily be just resistance. It might also include some inductance or some capacitance. So that's important to note. And so the question is, what load, in this case, do I connect in order to maximize the amount of power that I get at the load? And so again, this is my VS. This would be V out. All right. And so the case for AC is that power is maximized when ZL is equal to the conjugate of ZS, the complex conjugate. What does that mean? Well, that means that if ZS, for example, is equal to some resistance plus J times some reactance, ZL needs to be equal to that same resistance minus J times that reactance. And what ends up happening in that case? Well, if that's the case, and I look at my current flowing in this circuit, I would have to add ZS to ZL to get my total impedance. And if you add ZS plus its own conjugate, which is ZL in this case, you get that the two imaginary parts cancel. You'll get R plus JX plus R minus JX, and the imaginary parts go away, and we're basically left with this same equivalent circuit where I just have two resistances and the reactances are actually canceling one another. Okay, so that is the case for AC circuits where we maximize the average power transferred from the source to the load, is when the source impedance and the load impedance are complex conjugates of one another. They have the same real part, but they have the opposite imaginary part, okay? And so the same would go for if the source was real minus J times X, then the load would need to be the real part plus JX, okay? And so there's several different ways that you can implement any given one of these, but I just wanted to touch on the fact that in your career, you'll probably see this question pop up, that maximum average power is transferred when the load and the source impedance match. So just so that you can see it maybe for the first time. If you have any more questions about this, please feel free to let me know. Maybe I'll put a question on a homework about it to give you some more some more insight and working with problems like this. But I don't want to take any more time on this part of the module because we are in such an accelerated 5-week course. I want to move on to the next topic. So I'm going to go ahead and end this video here. Please feel free to ask questions if you have them. And we're going to start 3-phase circuits in the next section of this module, which is really exciting stuff, very practical. And we'll go right to it. So I'm going to end this video here.